Hi there, it's Mr. Pope from Winter Grammar School for Boys, and today we'll be looking at measures of central tendency and measures of spread. Okay, so this is the second session we're going to be doing with statistics, and what we're going to be doing hopefully is looking at different types of data and trying to infer from them some statistical values that are meaningful, i.e. they actually tell us something that's going on as a representative quantity of the data set. So let's recap some of the things that you should be familiar with already. So a couple of things that I want to talk about, the measures of central tendency. There's the mean, the mode and median. And by the way, when we say the mean, we tend to mean the arithmetic mean. Okay, there's a geometric mean as well, which is quite interesting. I'm sure I'll cover that soon at some point. But generally speaking at school, when we're talking about the mean, we're talking about the arithmetic mean. And I want to define a few things first. So when I use this sigma, as you've probably seen before in my videos, this just means the sum. So when I say the mean is the sum of all the values that you have and then divide by n, where that's the number of values. Okay, so x are the values in your data set and n is the number of values. Okay, so let's take an example of that really quickly. Let's say I've got the numbers 1, 2, 3, 4. Then x, well, let's concrete this. Let's say I've got xi, where xi goes from 1 up to n. So it's all the numbers. So this is the first number, this is the second number, this is the third number, and this is the fourth number, where n equals 4 because there's 4 numbers. And just to not confuse you, let's say it goes 1 to, well, let's say it's 10, 20, 30, 40. So there's 4 numbers, so n is 4. What we're saying is x1 is 10, x2 is 20, x3 is 30, x4 is 40. So the mean of those numbers would be summing up all of the x values. So 10 plus 20 plus 30 plus 40. And then you divide by the number there are, which is 4. And in this example, the mean, which we'll call x bar, okay, is going to be 25. By the way, just as a little side note, what happens if your data is grouped? For example, I've got 0 to 5. Well, let's make it a bit more concrete than that. Let's say it's greater than or equal to 0. Whoops. Up to less than 5. Let's say 5. Let's say to 10, and then 10. Up to 15, and then let's say 15. Up to 20. This is my x column in kilograms, say. And this is my frequency. There's 2 there, 5 there, 6 here, 5 here. Well, first of all, if they're grouped like this, then you would need the midpoint of each one, so 2.5, 7.5, 12.5, 17.5. And then what we would do for grouped is we would do the sum from 1 up to n of xi, the midpoint, and then that would be times by the frequency, multiplied by the frequency, and then it would be divided by n. So we would do 2.5 times 2, which is 5, 7.5 times 5, which is 37.5, 12.5 times 6, which is 75, I believe, and 17.5 times 5, 50, 85, 87.5. And then you add all those together. That's 80, 160, 175, 205, and I'll divide 205 in this case by the sum of the frequencies. So it's not n, it's the sum of the frequencies from 1 to n. So 2 plus 5 plus 5, that's 18. So 205 over 18 is approximately 11.39 to 2 decimal places. So the mean for this is approximately 11.39 to 2 decimal places. Okay, so I mean, this is more or less GCSE. You should be fairly familiar with this stuff. The only thing that's going to be a little bit new is this notation. And this sigma stuff just means the sum of. And the bottom index just tells you where to start, and the top one tells you where to finish. And if you really wanted to, you could put I equals n at the top like that, where I is the counter everywhere. But we generally don't do that because, you know, your counter rarely changes from the bottom of a sum to the top. So we'll just leave it as that. Yeah, so let's change this to black. So this is for grouped data, and this would be, I guess, for ungrouped data. Okay, the mode is really easy to sort out. It's just the most common data point or group. There's nothing fancy here. You just have to pick the group that's the most common, if it exists, and that's the one you pick. Now the median, there's a little bit of controversy, and well, I'll talk to you about that here now. Now, the median is defined to be the middle positions, the middle position of the data sets. That's it. It's the middle position of the data set. If you have that in mind, you won't go wrong. Now, here's the problem. There's two types of data that is going to change how you calculate this. One is if you're dealing with discrete data, and the other is when you're talking about continuous data. Now, I think I talked about this before. Discrete data is in packets, whereas continuous data is on a continuum. Now, if you want to work out the median, if it's continuous data, that's easy. You take the number of points in your data set and you divide it by 2. Now that's really simple. Now here's the controversy. Now for discrete data, the way I'd explain it is it's always m plus 1 over 2. You just add 1 to it and divide by 2. The reason for that is, let's say I've got 1, 2, 3, 4, 5. Okay, there's 5 data points. And if somebody was to ask you which one is the middle, I'm hoping you can just tell by inspection it's number 3. Now, here's the problem. The NXL textbook defines it a little bit differently, and I don't think it would be wrong in this example, but something in it just doesn't sit quite well for me. So yeah, if I wanted to find the median for discrete data, they're saying that I should divide. They should divide n by 2, so no n plus 1 stuff. And if this is a whole number, so if this is a whole number, then the median is halfway between this and next number. And if it's not a whole number, then they're saying automatically round up and then pick that number, which just seems like extra steps. But in this example, let's just see how that plays out. So if my n is 5, 5 over 2 is 2.5. That corresponds to it not being a whole number, because 2.5 is not a whole number. So I would round 2.5 up to 3. So I'd pick the third position, 1, 2, 3. And in this case, it will pick the median as well. Now, it's up to you. Now, the textbook for Edexcel does this as well for quartiles and percentiles. And yeah, with small numbers, it seems to make, it works out. But for me, it just seems a little bit of just extra silliness when you can just jump to the chase and just do n plus 1 over 2. The reason why I prefer that is because, well, just look at the example. I want the third position out of 5. If I take 5 plus 1 and divide by 2, that's the third position. Done. If I have 3 objects, I want the middle, so that's the second one. 3 plus 1 all over 2 is 2. Done. If I've got 99 objects, then the middle position is clearly 50, because then there's 44 objects both sides. So 99 plus 1 over 2 is 50. It just seems to work out. You can convince yourself otherwise. This whole just taking n, dividing by 2, and then these little rules, like if it's a whole number, then the median is halfway between this and the next number, and if it's not a whole number, you round up and so on. It just seems like a little bit of a fudge. So anyway, take of it what you will. The point is, if you stick to the median is the middle position in the data set, you won't go wrong. Okay, now here's an example. If you want to, pause the video and give it a go yourself, just to make sure everything's okay. Do it in a second. Okay, the frequency table shows the number of breakdowns B per month recorded by a road haulage firm over a certain period of time. Part A, write down the modal number of breakdowns. Well, the mode is the most common, i.e. the one with the highest frequency. That's clearly 2, so the modal breakdowns is 2, because that's got the highest frequency of 12. Okay, find the median number of breakdowns. Right, so how many breakdowns have there been? Well, 8 plus 11 is 19. 11 plus 12, I believe, is 31. Plus 3 is 34. Plus 1 is 35. Plus 1 is 36. Well, we can do it in two ways. You can do 36 plus 1 over 2, because this is discrete data, because you can't have any number on a continuum of breakdowns. You have to have 0, 1, 2, 3, 4, 5, and so on. So 36 plus 1 all over 2 is the 18th and a half position. But if we'd done it the Edexcel way, we'd do 36 over 2, which is the 18th position. So according to them, because 18 is a whole number, that must mean the median is halfway between the 18th and the 19th position. And in both cases, that corresponds to the 18th and a half position. So where is that going to be? Well, if we go from 8 to 11, if we go from 0 to 1, we've gone from 8 to 19 breakdowns. So that means the 18th to 19th one is between the last and second last lot in this one. So that means the median number of breakdowns is 1. The median, if we was to list them in order, then, as we go along, we're going to reach the 18th and a half one in the 1 category. Calculate the mean number of lockdown, lol. Well, that's going to be quite easy as well. If I do the sum up here, 0 times 8 is 0, 1 times 11 is 11, 2 times 12 is 24, 3 3s are 9, 4 and 5. If I add them all together, I will get 53. And if I do 53 divided by 36, I will get 1.47222222, which I'll take as 1.47 to 2 decimal places. By the way, if you have the calculator FX991EX, you can actually work this out. Well, your calculator has an input function to do this. And the way you do that is you press Menu, and then you go down to option 6, I believe, or 7, I can't remember which is the one that is table. You click on the table, you enter in your X and your Y values, where X is breakdowns. If you haven't got a frequency column, then what you need to do is clear all that, press on, and then shift menu, go to statistics, and then turn frequency on. It should say either on or off. And then once you input this data using menu and then option 6, I believe, and then put in the correct columns in for X's. So this will be your X column, this will be your frequency column. Then once you pressed equals on the last one, you press AC to clear it. It should say one statistic variable, one stat variable, one variable statistic. And then on your calculator, you press the Optn button, the OPTN button, and you should get a list of things you can do with it. One of them's like edit, one of them's data, and one of them is one variable calc. Press on that, and you want to get, if you want the mean, then it's denoted by X bar. Okay. In a brochure about how many loads reach their destination on time, the firm quotes one of the answers A, B, or C as the number of breakdowns per month for its vehicles. Write down which of the 3 answers the firm should quote in the brochure. Okay, in a brochure about how many loads... Okay. So, should you... Okay, so which one of these is valid? Well, the mode is 2. That's what happens the most often. But in the context of the mean and median, 2 seems a little bit too high. Also, in the context of this, maybe a haulage firm doesn't want to use its largest value to represent how many times their lorries or their loads break down. Next up, the mean. Why is that not a good idea? Well, to say you break down on average 1.47 times, that, I mean, as mathematicians, we understand what that means, and we understand that has come from a process of dividing, which is how we calculate things by a mean. But if you was to say, well, on average there's 1.47 sheep in this field, people would look at you a bit funny. And that's because the data is discrete. We're expecting a whole number. So I would probably choose as my answer the 1. Because 50%, it's dead in the middle of all the distribution. It's a whole number, so that's in context of the data type, which is discrete. To be fair, there's arguments to be had of all of them. I'm just going to go for 1. I think as long as you argue the case and you give a valid reason, it should be fine. Although Edexcel like to play silly games and do various other things. As a side note, and it won't be so much important for A-level maths, but generally in statistics, we're going to be looking at samples and we're going to be looking at populations. Okay, and the reason is samples are, well, if there's a large population and you take a sample from that population. So when we're looking at the mean, for a sample we would use X bar to denote the mean, whereas a population we would use mu. And for what we're going to be talking about in a second, which is the variance, for the sample we would use S squared, and for the population we would use sigma squared. And now it's very important to note these things are called parameters and these things are called statistics. Okay, it's very important that you get that early on, because later in life when you go to university, hopefully, and if you ever do statistics, you'll learn about biased and unbiased operators, and it essentially, these statistics can be biased or unbiased because they're not truly reflective of the population they come from, and hopefully you can see that just by inspection. For example, if I've got a number line here, 0, and I don't know, I've got a load of points, data points that say one there, 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 and the mean works out to be 0. But let's suppose I take a smaller sample of, say, these 3. So the mean for this population would be about 0, but the mean for the sample might be about here on the number line. It might be a negative number, and clearly, you know, it's biased because of how you took the sample. They're not necessarily the same thing. You learn how to correct that to some degree later on. Okay, interpolation. Right, now this is important because interpolation is a really cool idea that essentially it's an estimate. Okay, that's the key thing. So the idea is that when we have data, let's say I had a group 0, x to 5, and then 5 to 10. And let's say I've got this amount of data, let's say 1, 2, 7, 8, 3, 4, 8, 9. What would that correspond? Well, I've got 1, 2, 3, 4 here, and I've got 1, 2, 3, 4 here. Okay, so that's where the data set came from, and this is how I'd represent it in a grouped table. But suppose I have lost the original data because I have what's called summarized data. I just have the summary of it. And look what happens. To work out an estimate for the mean, I took the midpoint, i.e. 2.5 and 7.5, and I times them across to get a new column, and then I summed this and divided it by the sum of this, which is 8, and so on. What I'm actually doing there, the reason why it's an estimate, is because I'm saying I don't care what the actual values are. I'm just going to take this class from 0 to 5, and if there's 4 things in it, I'm just going to assume that there's 4 things at 2.5, the middle point. I'm not going to pretend like there's multiple ones. I don't care how it's distributed. I'm just going to say on average they all even out to the middle, the median. So you're grouping, you're saying that this group, you know, on the whole behaves like the median. And that's why it's an estimate, because it might not have been the median. For example, the 4 things in here might have all have been 0, 0, 0, 0. And all 4 things here might have been 9.9, 9.9, 9.9, 9.9. And that wouldn't have necessarily given the same mean as, say, it was 1, 1, 1, 2 or 5, 6, 7, 7, for example. It just depends. Now, here's the next thing. Suppose we don't just want, now what we use this for is not just the median, the mean, but it's the median, but also the lower quartile, which is the bottom 25%, the upper quartile, which is the top 25%, and generally percentiles in general, which means up to and including that percent. So for example, if I say you're in the 90th percentile, if you're in the 90th percentile, that just means that you're well, it's up to and not including, isn't it? Up to that percentile. If you're in the 90th percentile, that essentially means you've beaten 90% of other data points, i.e. you're in the top 10%. Okay, and now for the lower quartile we use Q1, for the upper quartile we use Q2. Percentiles we just use a percentage sign, there's nothing, you know, the percentile. And then for the median we use Q2. Oh geez, the upper quartile we use Q3, silly boy. lower quartile is the first quarter, upper quartile is the third quarter, the median is the second quartile. And now Edexcel like to play silly buggers again here. For continuous data, it's as you'd expect. So for continuous data, then it's just n over 100 times by the percentile that you actually want. So the lower quartile, if you think about it, is the 25th percentile, upper quartile is the 75th percentile, and the median is the 50th percentile. So if I wanted the lower quartile, so if I wanted Q1, that would just be n over 4. If I wanted Q3, that would be 3n over 4. If I wanted the median, that would be Q2, that would just be n over 2, and so on and so on. If I wanted the 30th percentile, then I would do n over 100, and then I'd times that by the 30 percentile. So that's 3/10 of n. Now, unfortunately, Edexcel does it again. And for discrete data, then you could just do n plus 1 times by the percentage you want. Okay, so what do I mean by that? So if I wanted the lower quartile, it'd be n plus 1 times by, well, the bottom quartile is just 1/4, or 25 over 100. So that's quartile 1. If I wanted the upper quartile, it'd be 3/4 of n plus 1. If I wanted the 45th percent, that'd be 45 out of 100 times n plus 1. So that's the 45th percentile. This is the upper quarter, and so on. Now, Edexcel do a similar thing here. The way they say it is they just go, okay, divide by the thing. So you don't have to do the end. So for what Edexcel want, and by the way, it will work the same. It's just one. It's a preference of how you want to do it. So Edexcel literally just want n divided by, or n times by, the percentile you want, and then it's this same whole. If it's a whole number, then you take the value in between this and next position up. But if the position isn't a whole number, then you take the value after rounding the position up, which is not nice, but there you go, Edexcel for you. So you can either just do n plus 1 and then times by the fraction of the data set that you want, or you can just do n times the fraction that you want, and then remember these games that if that position is a whole number, then it's halfway between the next position up and so on. And if it's not a whole number, then it's the value after rounding the position up. It's not great, but hey, there you go. So let's try an example. Again, pause the video should you want to. Pause it now, sorry, I've just hidden it. So, a roadside assistance firm kept a record over a week of the amount of time and minutes people were kept waiting for assistance. The times are shown below. Find an estimate for the mean wait time. Okay, so I'm going to use my calculator now. Unfortunately, menu, and I want to go to statistics. I need to set it up first. A shift menu. Where's my statistics? Menu, statistics. Let's try shift setup. Okay, so the midpoint of the first one is 25, then 35, then 45, then 55, then 65, and that will do. And then the frequencies are 6, 10, 18, whoops, 18, not 8, 18, 13 and 2. I want to do a calc. I want one variable, and it looks like the mean from this is 43.979, which is 98, and this is in minutes. Okay. Let's just double check I've done everything right. So I would have had 25 times 6, which is 150, plus 35 times 10, which is 350, plus 45 times 18, which is 810, plus 55 times 13, which is 715, plus 65 times 2, it's 130. Add all these up, so 130 plus 715, oops, 715 plus 810, 350 plus 150. That equals 2,155, and there's a total of 6 plus 10 plus 18 plus 13 plus 2, which is 49, and 2155 divided by 49 is 43.98. Yep, cool, I'll take that. Calculate the 65th percentile. Okay, so what would that be? I'm just going to do it my way, just because it's quicker. Well, I know there's 49 data sets, so n plus 1, so 50, times by the 65th percentile, which is 65 over 100. Okay, so 65 over 100 times by 50, we're looking at the 32nd.5th position. Right, now let's look at this carefully. 6 go up 10, we're now at 16. Go up 18, I believe we're now at the 34th position. So that must mean the median is somewhere in here. Now, how could you get a good estimate of that? Well, what you do is you look at the boundaries of the class. Okay, so between 40 and 40, can you see how this is 40 and this is 40? So if the lower end is 40, and here 50 and 50, they're the same. If it wasn't, say for example this was 39 and this was 51, then the boundary of the class would be 50.5 and the boundary of this class would be 39.5. So I'd do my diagram from 39.5 to 50. But because the boundaries of each class are right up next to each other, I can just take the lower bounds of each class. That's fine. And the median, or the 65th percentile, let's call it x 65th, like that, is somewhere here. And now, if I look at the frequency, the first 16 are down here. So that means if we start at 16, and it goes up to 34, which is up here, then from here to here should be 18 wide. 34 minus 16 is definitely 18. And this is continuous data. Oh, I did it again. So technically I could have any frequency between 16 and 34, but I'm interested in the 32.5th one, which is over here, 32.5. And now I want it so that the ratio between here and here, for both of them, is the same as the ratio from here to here. So really easy. 50 minus my x 65th over the whole thing, which is 50 minus 40, which is 10, must equal my 34 minus 32.5 over the whole, which is 34 minus 16, which is 18. And now I just make x of 65 the subject of this. Well, if I times, 34 minus 32.5 is 1.5. Divide that by 18. that is going to be 3 over 36, which is 1/12. So 50 minus x 65ths 10 times by that, so it's going to be 5/6 equals 50 minus. So actually, x 65th percentile is 50 minus 5/6. 50 minus. Whoops, daisy. So I will take that as 49.2 to 1 decimal place. So the 65th percentile is approximately 49.2 to 1 decimal place. Okay, the firm writes the following statement for an advertisement. Only 10% of customers have to wait longer than 56 minutes. By calculating a suitable percentile, comment on the validity of this claim. Okay, if 10% of customers have to wait longer than 56 minutes, then really we need to find the 90th percentile, where only 10% of them beat that, the rest of the 90%. So, same deal. M plus 1 is 50 times by 90%, which is 0.9. That's the 45th position. Okay, well, clearly the 45th position is going to be in the 50 to 60 column. So same deal again. This is 50. This is 60. And the 45th position is going to be somewhere. Let's call that X to 45. And then the group below it, if this is 34 plus 13, that's going to be 47, isn't it? So the numbers go from 34 up to 47 because it's 13 wide. And the 45th one actually is up here. So if I get it in scale, this X should be up to here. Okay, same deal again. This ratio must be the same as this one. So the oranges are over the reds, right? Because that's what's going on here. We've got the reds on the bottom. We've got oranges on the top. So we're going to have 60 minus x over 60 minus 50, which is 10, equals 47 minus 45, which is 2, over 47 minus 34, which is 13. So 60 minus x equals, times by 10 both sides, is 20 out of 13. So x is going to be 60 minus 20 over 13. And 60 minus 20 over 13 is 58.46 minutes. Right, so actually, only 10% of our customers have to wait longer than 56. Well, actually, that's pretty reasonable, because only 10% of their customers apparently wait 58.46 minutes or longer. So 56 minutes isn't technically accurate. That's actually probably a larger percentage, probably only have to wait 56 minutes or more. So yeah, actually, it's not true. It's a higher percentage. And if you wanted to work backwards, that's a fun little trick. So what could we have done? We could have gone 60, and then that's 56 is here. This is 50, and then we want to find the position. Let's say X, and this is 47, 34. So same deal again. This distance, 60 to 56, is 4, over 60 to 50 is 10, equals 47 minus X, over 47 minus 34 is 13. Times by 13 both sides, so that's 52 over 10 equals 47 minus X. Make X the subject. X is 47 minus 52 over 10. 47 minus 52 over 10. So actually, it's the 41.8th position. And 41.8th position for 49 people. Well, you've got to add 1, don't you? Yeah, so we're working backwards. So 50 divided by, or 50 times by what thing for the percentile equals 41.8 if we was to work backwards. So 41.8 divided by 50, so actually it's 83.6%. So actually it looks like 16.4% of people have to wait 56 minutes or longer. So actually there's a fairly larger percentage that do have to wait longer. And by the way, this idea of, and I've used the wrong colours, haven't I? This idea of taking ratios and kind of estimating where certain percentiles or quartiles are, this is called interpolation. Whenever you're trying to smooth out things or estimate where certain values are within a data set, that's called interpolation. But when you're trying to do the same thing outside of a data set, that's called extrapolation. So yeah, interpolation, this kind of ratios business, a lot of people don't get, but I honestly don't think it's that bad. It's just scaling things up and ratios and that kind of thing. Yeah, I think that's all I want to say on that. Okay, standard deviation and variance. Right. What is standard deviation? Standard deviation. Well, standard is another way, well, it's just average. Standard length of something, the average length of something. The standard time, it's just another way of saying average. And deviation is difference. If something's deviating from something, it's different from something. So what we're saying is the standard deviation is like saying the average distance of each point in the data set from the mean. Okay, so if you took every different data point and you found the distance between that data point and the mean, then the average of all those distances would be what's called the standard deviation. And it's a measure, whether it's a statistic or parameter of a data set, and it's just a measure of spread. So if something has a large standard deviation, that means the average distance from the point. Let's just do a sketch. So let's say I have a data set where the standard deviation S is small. What does that look like? Well, let's say the mean is this X with a cross, and all the other data points are fairly clustered around it, like so. But if S was large, i.e. the standard deviation was large, then what would that look like? Well, you'd have your mean here, but then you'd have the points scattered, the average distance from each of the points to the mean is a lot larger. So, I don't know, let's move this out of the way, let's put that there. Let's say I've got this, and we'll turn this red, say, not red, orange. So if S is large, then the data points are on average further away the mean, like so. So you can tell how a data set is spread out just by looking at the standard deviation. The range isn't necessarily a good measure of spread, although it does work. So quantifiably, by the way, and the variance is really easy to work out. The variance is just the standard deviation squared. So it's S squared or it's sigma squared. So whatever value we get for the standard deviation, we just square it and that gets the variance. I mean, they're very interlinked. Okay. So, how do we calculate the standard deviation? How do we calculate S? Okay, so here's the deal. what would be the difference between a general point x and the mean? Well, we just subtract one from the other. The problem with this though is if we were to do this for every data set, for every point on the data set, some differences would be like positive, like 2, some would be -3, some would be 2, again, one might be -4, one might be 5, and so on and so on. And here's the problem with that, and then another one but -2. Now look, if I took the average of all these things, I've got a 2, 2 and 5, which is 9, and I've got a -2, -4, -3, which is -9. So when I add these all together up, that's 0. So if I'm not careful, even though all these data points are scattered around the mean, their average distance, or the difference, sorry, not the distance, the difference is 0. So if I was to leave it as it is, then the average difference between any point and the mean would be 0, and that's clearly not what's going on. So the way we fix that is we say, okay, we take all these things, square it to force them to be positive, and then we take the positive square root of them, because squaring and square rooting kind of undoes it. By doing that, we're actually taking the positive root. So essentially that's just a posh way of saying, well, what all the differences are, we're just going to make them positive. And then finally, it should have been noted that we need to sum up all these things and divide by how many things there are to take the average. Okay, that is the standard deviation, right? So this bit is the distance between each points. We're summing up each of the points from I up to n, and then we're squaring that to make it, well, first of all, we're squaring, we're finding the difference, then we're squaring it to get the distance. We're summing all those things up, dividing by n and square rooting, and they'll undo that process. Okay, and make it positive. Okay, now you're probably thinking, okay, that's great, but then what happens if I don't know the mean, or I've just been given summary statistics? Well, let's suppose I expand out the top bracket. So I've got the sum of, now I've got xi squared minus 2 lots of xi x bar plus x bar squared. Okay, and this is all over n. This is square rooted. Okay, well, we can sum up the individual things and that will be okay. So this will be the square root of the sum of xi squared over n minus, now x bar is just a constant, so this will be x bar over n. We can take that out as a constant. This is going to be 2 lots of this, and this is going to be the sum of xi. And then plus, and then the sum of x bar squared over n, like so. Okay, right, what's going on here? Well, first of all, what is x bar? X bar is the sum of xi over n. So I can replace this, so it will become the sum of xi squared over n minus 2 lots of, now x bar is the sum of xi over n, but there's another n pointing here, so that's going to be over n squared, and because I'm multiplying it by the sum of xi again, this is going to be sum of xi squared, like so. Okay, now notice the sum of xi squared is not the same as the sum of xi all squared. Okay, if I take this one, okay, let's say we're dealing with 1, 2, 3, 4. then the sum of xi squared means you square the x's first and then sum them. So this will be 1, 4, 9, 16. You add them together, 1 add 4 is 5, 9 and 16 is 25, so that will be 30. Okay, now sum of xi and then square it means you take the sum of the numbers, so 1, 2, 3, 4. You sum them first and then square it. So 1 plus 2 plus 3 plus 4, it says 10, isn't it? And so when I square it, that's going to equal 100. Can you spot how these two things are not the same? They're doing different things. That's important. So if I go over here, let's think about it. Now the sum of x bar all squared means I've got x bar all squared from 1 up to n. So I've got n lots of it. So this is going to be plus n times the sum of x over n, but then this is squared and this is squared, and then don't forget this n here, so that n's going to go here like that. Right, so what's going to happen? These two n's are going to cancel, so goodbye, goodbye. And now, actually, I forgot the xi here. And now, when you look at it a little bit carefully, this is going to tidy up nicely to the sum of xi squared over n minus the sum of xi over the sum of n squared, like so. And now notice, if you're given summary statistics of the sum of x squared and the sum of x, these are the only two things you need in order to use the standard deviation of this form. Well, and also you'll need n. This is really important. This is the alternate form of standard deviation. And to get the variance, you just square the whole thing, so you just get rid of the square root sign. Okay, now this is for ungrouped data. Now you can prove pretty much in the same way, so let's deal with grouped data. Now grouped data is very similar, but in terms of n, there is no n, it's just sigma f now, because you have to sum the frequencies. So in the same way, the standard deviation can be written as, and I'll just give the better version down there of it, it's the sum of x squared f over the sum of f minus the sum of xf over sum of f squared. Okay. So, generally speaking, these orange ones, these orange formula are the ones you need. In some textbooks, they'll refer to this quantity, i.e. the sum of the x's, xi's minus x bars, as s small script x small script x. And your calculators, you'll see that as s of x like that. Sometimes. It just depends. Depends on the calculator. If you've got one like Texas Instruments, maybe some of the older Casio ones. But yeah, in terms of standard deviation and variance, yeah, to calculate them, you just follow those rules. The reason they are those rules is because, as I said, they're the average distance away from the data point. And yeah, I mean, I can leave it up to you why the group data one as it is, but you can probably actually see the similarities of why it would work for each one. And the analogy is the sum of f, the sum of the frequencies, is the number of data points. Yeah. Okay, so here's some examples. If you want to pause the video and give it a go yourself, be my guest. Just going to have a little sip. Okay, right. So for a set of 10 numbers, the sum of x is 50, the sum of x squared is 320, and for a different set of 15 numbers, the sum of x is 86, the sum of x squared is 568. Find the mean and the standard deviation of the combined set of numbers. Right, so let's deal with this. The combined sum of the two numbers which we'll call sigma of capital X, is going to be 50 plus 86, which is 136, isn't it? And then the sum of capital X squared is where we sum these two. So 310 plus 356, 568, sorry, what am I talking about? 568, that is 878. And now the mean is just going to be the sum of x over n, which is clearly 136 over the total combined set, which is 25. So 136 over 25 is going to give 5.44. And then the standard deviation is the sum of x squared over n minus the sum of x over n, all squared, square rooted. This thing, if you think about it, is just going to be capital X bar, which we've done before. So it's going to be the square root of fraction sum of x squared, which is 878, over n, which is 25, minus the 5.44 squared. Yep. Okay, and this means this standard deviation is 2.35 to 2 decimal places. So first key bit, the standard deviation always has to be positive. You can't have a negative distance away from the mean. So if you get math error, it's probably because you've made a boo-boo here, you've switched these round, you've not memorized them the right way. I wouldn't personally rely on the formula book. I just wouldn't look at it. I think they're pretty easy enough formulas to figure out on your own. To be honest, you can derive them if you just think about it really quickly. It doesn't take too long. Okay. Nahab asked the students in his year group how much pocket money they get per week. The results rounded to the nearest pound are shown in the table. Use your calculator to work out the mean and standard deviation of the pocket money. Give units with your answers. Okay, the mean is the sum of xf over the sum of f, just like we've done before. So you can either use your calculator or you can just do it the long way. So you can have 8 times, so let's make an xf column down here, or a row in this case. So 8 times 14 will give 112, 9 times 8 is 72, 10 times 28 is 280, 11 times 15 is 165, and 12 times 20 is 240. The total frequency is 14 plus 8 plus 28 plus 15 plus 20. So sum of f is 85. So out of 85, I've got 112 plus 72 plus 280 plus 165 plus 240. So 869 divided by 85. It looks like 10.22 to 2 decimal places. Use your calculator to work out the mean. So the mean, x bar in this case, is going to be 10.22. And the standard deviation, S, is going to be sigma x squared f over sigma f minus sigma xf over sigma f squared. So this is going to be, right, so I need to work out sigma x squared of f, I need to do 8 squared, so let's do this, x squared f. So I do 8 squared, which is 64 times 14, so that's 896. I do 9 squared, which is 81 times by 8, which is 648. I do 10 squared, which is 100 times 28, which is 2800 or 2800. 11 squared is 121 times by 15, which is 1815. And 12 squared, which is 144 times by 20, is 2880. Sum those all up, so 896 plus 648 plus 2800 plus 1815 plus 2880. That is going to be 9039 over sigma f, which is 85, minus our mean, which we worked out before. I'll leave it as the exact fraction, 869 over 85 squared. All I have to do is bang that into a calculator. So fraction 9039 over 85 minus fraction 869 over 85, close brackets, squared. And this apparently is 1.35 to 2 decimal places. The average difference, and this is in pounds, so the average difference away from £10.22 is £1.35. So another way of looking at that is if you are outside of the range £10.22 plus or minus £1.35, that's quite unlucky really. Okay, how many students give units with your answer? Well, there you go, it's in pounds. It's almost forgot. Part B, how many students received an amount of pocket money more than one standard deviation above the mean? Well, that's going to be 10.2 plus 1.35. It's 10.22 plus 1.35, 7.5. So 11.57. So how many students read and received more than one standard deviation? Well, it's all the people that got 12 or more. So that answer is 20 students. Okay, cool. So standard deviation and variance, they are just measures of spread, and they are literally the average distance or difference of each point in the data set from the mean. Okay, coding. Right, now what's the point in coding? Well, sometimes data is either too big or unwieldy, or it's just generally not nice to work with, and we can perform linear transformations or linear coding to data to make it easier. I'll take an example. Let's say I've got 1 million, I've got 2 million, I've got 3 million, and I've got 4 million. Now these are all big numbers. Let's say this is my data set X. Then I could say introduce a new data set, so I could introduce a coding, let y equals x divided by a million. And now this will mean that y is the data set of 1, 2, 3, 4. And all of a sudden it's really easy to work out what the average of y bar is. That's just 2.5. And then now I can reverse the coding and say, well, x bar is just where I times that across. So x bar is 2.5 million. However, you're going to have to be really, really careful when it comes to the standard deviation. Okay, now the standard deviation is not so straightforward. So what do I mean by that? Well, put it this way. The standard deviation of these numbers is just going to be the sum of y squared over n minus the sum of y over n all squared. So that's going to be the sum of y squared. So 1 plus 4 plus 9 plus 16 is 30. Over how many there are? 4. Minus the mean squared, which is 2.5 squared. So square root of that thing is 30 over 4 minus 2.5 squared. And this turns out to be 1.118. Right. Now, is it necessarily a case that we just multiply this 1.118 by a million? Is that necessarily true? Yes. Let's think about it. 1.118, if we times it by 1.118 million, is saying the average distance between these points is 1,118,000 away from 2.5 million. That's totally okay. But let's suppose I had the variance s squared, which is that number squared which turns out to be 1.25. Now notice, look what happened if I just had the variance. If I times that variance by 1,000,000, I will get 1,250,000. And then think about it. Let's suppose the variance of y, which I'll call let's say this is sy and this is sx squared. Let's suppose I didn't do that. Let's say I've got this now. Let's say I've got the variance of x is 1.25 million. Then look what happens if I was to square root that number. So if I was to have the square root of 1250000, this will give me 1118. Can you spot a difference here? Do you think that this data set here, they are roughly 1118 things away from the mean, which is 2.5 million? Well, no, that's clearly not right. So whenever you're scaling up this data, you've always got to do the multiplicative scaling to the standard deviation, to the standard deviation of y, not to the variance. The other thing to note is the following. Let's suppose I was to have a shift. For example, I've got the following. Let's say I've got 100, 1001, let's say I've got 1002, 1003, 1004. Okay, now same deal, let this be my x. Let's change this to a different colour. So what happens with shifting? Okay, well let's suppose that y is just going to be x minus 1000. So now the y data set is 1, 2, 3, 4. And then same deal again. We're going to know that y bar is just going to be 2.5, and the standard deviation of y is going to be 1.118 again. Now look, if I undo this process, then x is going to be y plus 1000, isn't it? Just by inverting it. I add 1000 to both sides. So if I add 1000 to get x bar, does it seem sensible for x bar to be 1002.5? Yes, because that would be here. It would be dead in the middle. But if the standard deviation of x were to be added by 1000 to be 1001.118, does it make sense that most of them are approximately 1001 spaces away from 1002.5? Well, no. Most of them are between 1 and 2 position, or 1 or 2 of a distance away. So this is a nonsense. What can we take from this? We can take from it that the standard deviation is only affected by multiplicative coding, i.e. adding or subtracting has no effect, whereas the mean is affected by both multiplying and additive coding. Right, let's have a think about why that is. Let's say I've got a number line. And let's say here's my data point. Let's say there's x, and I've got all my data points here, 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 and here. And let's say my 0 is about there. Now, if I were to add something to my data point, all my data points, then what would happen is this cluster would just move to the right. the average distance would stay the same. So adding and subtracting to my data set will just shift it left and right, for example. It won't actually change the average distance from each of the points to there. However, by multiplying, then essentially what you're doing is you're doing this. You're increasing it. Or making it smaller, increasing it, and so on. So only the multiplicative parts are going to make the average distances larger. Okay, that's a key concept. Later on, we look at discrete random variables and we look at expected values. We'll write this in a more formal way, but it's key to just get the intuition that the mean behaves like you'd think it would do with linear coding, but the standard deviation is only affected by the multiplicative transformation. So that's the last question I wanted to go through today. Pause it, give it a go yourself. Okay, a meteorologist collected data on the annual rainfall X at 6 randomly selected places. So n is 6, let's clear that up. Okay, the data was coded using S equals 0.1x minus 10. So you're dividing by 100 and then subtracting 10. The following summations were obtained. The sum of S was 16.1, the sum of S squared was 147.03. Work out an estimate for the standard deviation of the actual rainfall. Right, so let's work out the standard deviation of S first. Well, it's going to be the sum of S squared over n minus the sum of S over n, all squared, square rooted. So sum of S squared is 147.03. This is over n, which is 6, minus the sum of S, which is 16.1, over n, which is 6, and then that's squared. This is SY. Okay, so quick calculator bash. So, where is it? Fraction 147.03 over 6 minus bracket fraction 16.1 over 6, close brackets, squared. So we get SY is 4.1598, so actually it's 4.16. Okay, and that's millimeters. Okay, now let's think about this very carefully. Well, why do I say S? It's just, if anything, it's S of S, isn't it? Okay, now let's look at what's happening here. S plus 10 and then divided by 0.01 is going to be the same as timesing by 100. So it's 100S plus 10 times 100, which is 1000, equals X. So here's the deal. To get X bar, we would have to times the mean by 100 and then add 1000. That would be totally legit. But to find S of X, remember, addition and subtraction doesn't actually change it. It's this multiplying by 100. So it's going to be 100 lots of S of S. So all I have to do is times this number by 100, and the standard deviation of X, so the standard deviation of X appears to be 416 millimeters. Is that right? Yeah. So there you go. That's it. Right, guys. I hope you're having fun. See you tomorrow. Bye.